Okay, welcome to EE674. Right. So in the last part of the lecture, we derived the swing equation, and we saw how the the angular position of the rotor delta varies when you have the disturbance, the change in the load, maybe due to the outage or maybe due to some other reason, right? So how the swing angle of the synchronous generator will be the varies, right? And hence how uh, the the speed of the machine will vary. Okay, so now so in order to understand or in order to simulate these effects, how the frequency or the speed of the machine or the angular position of the machine varies based on the different disturbances, we will the model the synchronous generator and its associated the component, right? So then you will be able to model these in a MATLAB, Simulink, or the what you call it, Scilab Xcos, right? Which is the equivalent of the MATLAB Simulink. I will come to that later. So then you will be able to model it in detail, and you will be able to analyze it, the effect of different disturbances. Okay, so let's do the modeling part. Okay, oops, there's something wrong. Let me stop. Okay, so let's start the modeling part again. Sorry, yeah. Okay, so you look at the modeling of synchronous generator, and associated components. Right. So what are the components that are associated, or what are the things that we are going to model, right? So we will first model the generator itself, and then we will model the loads, and then we will also model the prime mover, and then the governor. Okay, so we are basically building the model for each of these physical components. So you know what's the model, right? Or models basically describe or basically represent the physical world, the real world thing in a mathematical, using a mathematical equation, right? So the models are basically, you can say, mathematical representation of the components. So this mathematical representation, you can derive it in different ways based on your requirement. When you are doing a steady state analysis, you come up with a different model. When you are doing a transition analysis, you come up with the different models, and so on, right? And there are various ways that you can do the modeling, right? You can model it in a state space form, right? okay, where the model will be expressed as a first order differential equation, right? So I would say model as a equations, okay. Or you can the model is in the block diagram form, where the derivation is in the Laplace domain, right? Okay. Uh, okay. So so let's look at the different components, right? So we will okay. We will model for the load frequency control, right? Okay. Uh, okay. So here the speed control, the frequency will be controlled by controlling the speed of the prime mover, right? Using the governor mechanism, right? So first, as I said, we will look at the generator model. Okay. So in the generator model, uh, so we will start from the swing equation, okay, without considering the damping part, right? So we have seen the swing equation, okay. We will use that as the basis of the load frequency control, right? So we had 2h over omega naught d squared delta over dt squared equals to Tm minus Te, okay. Now instead of torques, we will introduce the power terms. Okay, so we'll have 2h omega naught t squared over dt, change in the angle would be equals to the change in change in the mechanical power minus the change in the electrical power, right? So this is basically so as we discussed earlier, this is the inertia constant, and this is the synchronous speed or the rated speed. Okay, and here is the change in the angle. So the entire thing is the measure of the change in frequency. Okay. and this part basically denotes the increase in the power input to the generator. Right, so how much power it was supplying to the electrical load and how much power input to the generator. So the difference basically says the increase in the power input to the generator. Okay, right, so now okay. Now with the speed expressed in the per unit, okay, d over dt delta omega, that's the speed, is equals to 1 over 2h, right? So this is in per unit, right? That means you know, the omega over delta omega over omega naught, right? And so I am kind of you know, dropping that the bar here for ease of writing, right? So please keep that this is in the per unit. So this delta, the omega naught is inside, right? So that would be equals to delta Pm minus delta Pe, right? So and if you take the Laplace transform, so this is in the differential equation form or the state space model. So if you take the Laplace transform, you will have delta omega s in the Laplace domain. The change of the speed is equals to 2 h s times delta Pm minus delta Pe in the Laplace domain. Okay, so now if you represent this as in the block diagram form, so you have the mechanical input coming into the generator minus the electrical power or the load, right, coming from the load, electrical power output, and you have a gain block of transfer function block of 1 over 2 hs, right, and that will give you the change in the speed of the synchronous machine. Okay, right, so this is the speed variation. So it's depend on the electrical power output of the synchronous generator and the mechanical power input to the synchronous generator. Okay, okay, right, so that is the generator model, right? And so we will go one by one, and then we will combine all these models to represent the total effect, and then we will consider, you know, having many generations and so on, right? So then the second one, we will model the load, okay, for our study, right? Okay, so the speed load characteristic of a composite load or can be approximated by the equation that your load, the power supply to the load, equals to the non-frequency sensitive loads plus the frequency sensitive load, right? So this load is non-frequency sensitive. That's why it's called the composite load, and this part of the load represent the frequency sensitive load, right? So it's sensitive to the change in the speed or the frequency. Okay, right. So the D here is defined as uh, the percentage change in the load divided by the percentage change in the frequency. Divided by the change in the frequency, right? So that means how sensitive the load change to the frequency change, that is defined by the D, capital D, right? So in the Laplace domain we can write this equation. So delta PE, the change in the electrical power, is equals to delta PL, the change in the non-frequency sensitive load, plus the the D delta omega S, right? So which is sensitive to the change in the speed. Okay, right. So okay, so now you can see that there is a delta omega S part, which is actually the output of the generator model. So we can combine this load model with the generator model, right? So I would say including the load model in the generator model. So in the generator model we had that delta PM, right? This is plus, this is minus, right? Oh, you can write it inside also. This is plus, this is minus. Okay. Here we had delta PE is, okay, and the transfer function 1 over 2hs, which had the output delta omega s, right? And then in this equation you can see that the delta PE, that is this part, is equals to delta omega, right? Delta omega, that is this here, times the D, okay, that's, and plus this part. So you yeah, you can also yeah, you can add it in here as well, delta PLS, right? Okay. Actually, okay, I will go one step at a time rather than going straight forward, right? So here you can say that, okay, this d times delta omega s, right, plus the uh, delta PLS, right? So this is plus, right? And then here this is minus here, so you can take this delta PLS to here also. So this, then the entire block will become so you have delta PM is plus, and you take this one and you have a minus sign here, so that will also become a minus, so delta PLS, and this minus delta PES, right? Okay, I will write it here, delta PES, and then you have here 1 over 2HS delta omega S, and here you have the T, right? So this is the block diagram form with the generator plus the load, right? So generator attached to the load. Okay. So actually you can combine this path, right? So by using your control theory, right, or the block diagram simplification, you can simplify that to be PMS minus delta PLS times 1 over 2HS. That will give the variation in the speed of the synchronous machine. Okay. So now this is the generator plus the load model. Okay. So now okay, so now this the mechanical input, right? So that is actually coming from the prime mover and the generator model, right? So we will see how this the mechanical power is generated and how we can incorporate this in the our model, right? So in order to understand that, the first we will look at the prime mover model. Okay. So this is the source of the mechanical power. Okay. So this could be, you know, the hydraulic turbine or the steam turbine, or, you know, that's a source, input of the source. So it could be hydraulic turbine or steam turbine. Okay. Okay, so we will look at the steam turbine case, right? For the steam turbine, the prime mover model, okay, model of the prime mover must take the steam supply and the boiler control to the account, right? So it should consider both the steam supply and the boiler control, right? So there are various models depending on the boiler type, the prime mover type, the steam supply type, and so on, right? And the steam cycle and blah blah blah. So we will consider a very simple for a simplest non-reheating steam turbine. Okay, the transfer function of the turbine is given as the delta PMS over delta PVS is equals to 1 over 1 plus tau TS, right? So this is the transfer function for the turbine. Okay, and this is the time constant of the turbine. Right, so this is the mechanical power, and this is you have to something to do with the valve, right? So we will go to that when we are doing the the governor model. So this part actually coming from the governor model. So for the time being, we will consider the prime mover model, and then we will go to the governor model, right? So so it's very straightforward. So you can write the the output or the mechanical power okay depend on the power input from the governor or the valve, right? And the transfer function, corresponding transfer function would be 1 over 1 plus tau ts, right? So it's simple as that. And you can now extend your generator model, right, including the prime mover model as well. So you can either take this. So okay, sorry, here I think I have missed the plus d part here, right? I'm glad that I went back. So okay, so yeah, so when you're combining that, you have that plus d. So I missed that part. Okay, so please note that. Okay, so let's say I'm gonna take the yeah, so let's take this combined model, or this one. I would say combining the prime mover model with the generator plus load model, right? So you have the mechanical power input is now coming from the valve control, right? So this would be delta PMS, right? And it's coming from 1 over 1 plus tau TS and delta PVS, right? Okay, so now the question is, okay, where this the delta PVS, how we can model that and where it is coming from. So it is actually, as I said in the earlier, it has to do with the governor model, right? So for next we will consider the governor model. Okay. So here I have just pasted the governor. This is a mechanical governor system. Okay. So so if you look at the this system, when the when PE is greater than the PM, that is the electrical demand is greater than the mechanical power input, right? Okay, then the PM minus PE is the supply of the kinetic energy stored in the rotating system. Okay. Okay. So we'll come to this later. So when you have excess the load or the extra load, then the generator, the mechanical power input, the power is going to the load through the kinetic energy already stored in the rotating system, that is in terms of the inertia, right? And so this when it is supplying this kinetic energy, the energy stored in this system will be reduced. So the reduction of the kinetic energy basically slow down the turbine, okay, and hence the generator frequency will drop, right? And so when it's slowing down, this the turbine speed is sensed by the governor, and then it's adjusted the turbine input valve to change the PM, right? The mechanical power input, right? So it will adjust the valve so that the mechanical power input to the generator will be increased. Okay. So as seen in this the figure, the old governors are the mechanical, but the modern governors use electronics to sense the speed change and then turn on and off for the control the valve position by using the electronic means, right? So whatever the system you use, the speed governor mechanism act as a the comparator, right? Let's say the speed governor mechanism act as a comparator. Okay. And so what will happen here is the output power is the difference between the reference power and the power that is that is given by the group characteristic, right? So let's say like this. So it acts as the comparator whose output delta Pg, let's say, is the difference between the reference power delta P ref, okay, and the power defined by the droop curve, right, which is 1 over R delta omega, right? So this is the frequency sensitive part. So if you look at the frequency or the speed frequency, right, versus the power in per unit, so you have this droop characteristic which is R, right? So now depending on the speed or the frequency, the delta omega, right, you define what should be the power. Okay, so that is given by 1 over R, right? This slope or is called the 1 over R, that is this, right? So based on the based on the speed that you are running, you can get the power. Okay, so this then the output power of the governor, okay, delta Pg is equals to the reference power minus 1 over R delta omega, right? So in the Laplace domain, delta PGS is equals to delta P ref S minus 1 over R delta omega S, right? Okay. Okay. So this delta PG command, right? That's the output power command. So that would be transferred through the hydraulic amplifier, to the speed valve position control command, right? So in order to achieve the speed valve position control, right, so the command delta pg is transferred through the hydraulic amplifier, okay, to the speed valve to determine the speed valve position command. That is delta PV, right, which we have seen earlier. So you can write the if you assume the linear relationship and the considering the simple time constant, okay, delta PV can be written as it's a simple transfer function 1 plus tau gs, right, delta pgs. Okay, so now you can combine this model together, right? So if you just look at this equation here, you can model it as, so I will just copy this one. Okay, so let's consider, okay, this one, and okay, so that can be modeled as the so you have okay, you have your reference power, okay, input, right, minus the 1 over r delta omega s, right, that will give you the delta pgs, right, and then considering this equation, that times the 1 over 1 plus tau gs will give you the delta pvs, right. So now we have the valve position control command here, and then combining that with the our generator model, generator plus the prime mover plus the load model, right, the combined model here, you can generate, I would say, the hence the combined model you have that in here, right, and then you have this, right, and so it is coming like this, right. So I will erase this, hopefully I can do that, these unnecessary parts, yeah. So this is delta pvs, right? And then here you have the delta omega s, so that is basically coming from here, right? So that's the combined model. Okay, and here you have the governor model, right? And then here you have the turbine model. So let me get rid of this as well. Okay, and then here you have the generator plus the load model, right? So now you can see, based on the reference power, you get the relation how the speed of the generator will vary, right? With the variation of the load and the turbine and the governor control, right? Okay, so now this is, here you have the the reference power as the input, but what we are actually interested is the what will happen when the load change, right? So we can redraw this diagram. With load change, that is the delta PL is, that is this one, as an input, right? Change delta PL is as the input, and the frequency deviation, that is delta omega s, as the output, right? So we will get the delta PLS as the input. So you can try to derive this, right, by the block diagram simplification methods, right? So you have the because there is a minus here, so we will get the minus delta PLS, right? And you will get 1 over 2hs plus d delta omega s, and then here you will get the 1 over r times 1 plus tau gs times 1 plus tau ts, right? Okay, so this is the block diagram with now the load change as the input and the frequency deviation as the output of the model, right? Okay, so oops, sorry, something went wrong here. But yeah, this happens sometimes. I don't know how to fix that. Now I can't draw in here, so I will stop the video at this point, and then we will continue from there.